Let's take a look at traces of three-dimensional surfaces. We're going to use a tool in the Maple software called a tutor. If you have access to Maple, one of the menu headings is Tools. Under Tools, you can find something that says Tutors. And this has little, tutorials about different things that you can open up. And if you dive into the Multivariate Calculus submenu, one of your options is called cross-section, which is another word for a trace. And what you're seeing here is the default window that opens up. So I'm just going to show you a couple of pictures because traces can be kind of hard to visualize, and in a lot of cases I don't know if it's worth opening up a bunch of software to look at them, but at least you can get a sense of what they're supposed to look like. And in a lot of cases what we're doing is picking particular cross sections at particular values and looking at those. So here you just see the garden variety paraboloid, z equals x squared plus y squared. So that's the gray shape that opens up like an upside down umbrella. And then you see cross-sectional circles. So it's like a bread slicer or a pizza. We've just cut through the surface at different elevations, different values of z. And we look at, what does the shape look like at that cross-section. And this paraboloid being an, upside down umbrella, in this case, the cross-sections are circles. If the equation of the paraboloid is z equals x squared plus y squared, then at z equals 1, we would have the circle x squared plus y squared equals 1, circle of radius 1. At z equals 4, we'd have x squared plus y squared equals 4, circle of radius 2, and so on. And so it shouldn't be a surprise that we're seeing circular cross-sections. And one of the nifty things we can do with Maple is kind of, tip it around just so we can see what's going on. If we were to change the function, I'll just put a 3 in front of my y, and then ask, well, I guess it wants a multiplication sign. Okay, there we go. Now we should expect to see ellipses as the cross-sections more pronounced. I mean, circles are technically ellipses, but you know what I mean. And so there, some of these ellipses are now escaping the window, and I'm not going to mess with the bounds on the window, but we've made an elliptic paraboloid, and as expected, the cross-sections are ellipses because now the equations of these cross-sections are x squared plus 3y squared equals some constant z value, 1, 2, 3, whatever it is, and those are ellipses. So when you see an example that says figure out what this shape is using traces, just take the equation of the shape and whatever direction you want to slice in, just plop in some selected constant values because you'll take a function of 3 variables, plop in a constant value for one of the variables. Now you have a function of 2 variables, and odds are its equation is going to be one of your recognizable shapes like a circle, a parabola, a hyperbola, things like that. So if you know your conic sections, like your 3 or 4 basic conic sections, you'll be able to identify traces in these quadric surfaces as needed. Now, if you have some sort of wacky three-dimensional surface like z equals the natural log of x plus y minus 1 over e to the xy plus z, something crazy like that, the cross-sections are not going to be recognizable shapes. But in the quadric surfaces, they are. By the way, if you hear panting in the background, my dog is he's propped up in my lap because I was just eating lunch and he wants snacks. So that's what that noise is. That's not me panting. So I'm gonna switch the shape just so you can see something different. So instead of the z equals x squared plus y squared, I'm going to revert to z equals x squared minus y squared. You may know by now what shape that looks like, and if not, you're about to see it. I've got to change the levels of z that I'm going to look at because they will now be positive or negative. So I've changed some of the parameter values here. I'm going to ask for a new display. There we go. Okay, so if you didn't recognize it at first, z equals x squared minus y squared is your basic garden variety Pringle chip, otherwise known as a hyperbolic paraboloid. Now, why is this called a hyperbolic paraboloid? It's because the cross sections or the traces are either going to be hyperbolas or parabolas, depending on what direction you look in. So the light pink gray shaded thing is this three-dimensional surface. And then now I've cut through it at z values going from -4 to 4, and you can see those cuts in the surface. And if I tip it down, there they are. You can see the hyperbolic shapes that are being formed. I'll see if I can spread these out a little bit. Maybe do fewer of them. Waiting, there we go. Okay, so now you can see they're more spread out. So as you're looking kind of horizontally across, let's see the z-axis over here. So the z-axis going up and down in the box this way. So here's a constant z, constant z, constant z, and you're seeing the cuts in the surface that are created at those different z values, and those are hyperbolas. Now if I come over here and ask for cuts in the x direction, we should see the same shape, but now we've asked for cuts at x equals -3, -2, etc., etc. So we have the same kind of shaded overall Pringle-looking hyperbolic paraboloid as the surface, but now we're cutting vertically at constant values of x, and now you see that these cuts are forming paraboloids. And if you take the equation z equals x squared minus y squared and plug in a constant value for x, like 2, that would turn into z equals 4 minus y squared, which you would recognize as now a parabola. So the cut through x equals 2 gives us an upside down parabola in the yz direction. So here you're just seeing a sequence of these upside down parabolas. And that's why this is called a hyperbolic paraboloid, because the cross-sectional shapes are hyperbolas in some directions and parabolas in others. And again, when you're asked to determine the type of a shape based on traces, that's what you're doing. You're just saying, what if I slice through this thing at x equals 1, 2, and 3. What shapes am I going to see? What about y equals 1, 2, and 3? Or -1, -2, -3. What shapes am I going to see? And you can take the accumulation of shapes and sort of imagine what this whole surface is going to look like as a whole. Some are very predictable. Right? Here is going to be an ellipsoid for, this will take me a while to type in here, 4 times x squared plus, I got to make sure to put in my multiplications, 9 times y squared plus 36 times z squared equals 36. That's going to be the equation of this ellipsoid, and we're going to let x go from -2 to 2. We'll let y go from -2 to 2, and now z is actually in the mix, so let's take z from -2 to 2 as well, and let's do some horizontal cross sections. Let's say -1.5 to 1.5 in the z direction. That's going to be a grand total of what, 7? If I go every 1/2 of a unit, 6, 1, 2, 3, 4, 5, 7 cross sections. I could make any number of cuts as I wanted to. What do you mean? What does that mean? What is that? Oh, I missed that number there. Okay. This was supposed to be like a 5 or 6 minute video, and obviously it's running longer, but that's because we've been sitting and waiting for Maple to spin its wheels while it creates plots. But we've seen a couple, and this will be the last one we'll take a look at. So here is, again, the shaded shape. So we didn't quite capture the entire ellipsoid, but you can see the shaded three-dimensional football shape kind of thing. And then as we look in the z direction, we make cuts at z equals -1.5, -1, etc., etc. As expected, we are intercepting that surface with elliptical shapes. And because this is an ellipsoid, if we switched these to the, say, the x direction, now we'll see cross-sectional ellipses again, but this time they'll be vertical. So if we had no idea what this function, 4x squared plus 9y squared plus 36z squared equals 36, if we solve the equation, we say we have no idea what that shape looks like, well, we make some traces. We imagine constant values for x, a few constants for y, a few constant cuts at z, and we would see, hey, in every single direction we're cutting, we are getting ellipses, which means that put together as a whole surface, we are going to see an ellipsoid. So in this case, it's like a watermelon. When you cut across the thick belly of the watermelon and then separate it, you see shape, the cross-sectional cut is almost circular. But if you cut from one tip of the watermelon to the other long ways and open it up, you're definitely going to see an elliptical shape. Food always becomes a good example in multivariable functions. So I hope that helps. That's what's going on with traces. Your job in a lot of examples is just going to be to calculate what some individual traces look like and sort of accumulate graphical information about the surface. You're not asked to draw any of this. You just have to work with the equations.